Good afternoon, everyone. My name is Sijin and I'm the Senior Modeling Specialist from the Treasury. And you probably noticed that my title is quite different to what I proposed in the abstract. The reason is that I just can't finish that project. So I asked my boss, what should I present in this conference? And my boss just suggested, why don't you just use this opportunity to actually show some of the challenges of applying machine learning AI, like in the socioeconomic studies as a Treasury, and trying to say if there are any suggestions or support we can get actually from this community. I think that's a good idea. So the title is Opportunity and the Challenge of Applying Machine Learning in Socioeconomic Studies as a Treasury. And for people who don't really know what's Treasury, and probably you heard our name, when every year there is a government budget releasing process. So we're managing the government budget. At the same time, we manage the public debt, public investment. We provide the financial and economic advice to the government every year. And we are a central agency along with a few other agencies essentially to enhance the well-being across different groups of New Zealand. That's kind of what we're doing. And we have lots of data as a Treasury, and one of the data set is IDI, so it's from the integrated data infrastructure. So it contains all this uni-record data for every individual in New Zealand. It's provided by a wide range of government agencies and managed by States New Zealand. So we use this data a lot. We use it to do the tax transfer model. We use it to evaluate cross-domain impacts to inform policy and design. We use it for lots of other things. And so there are quite rich data set over there. And currently we're just using some quite traditional ways to do some trend analysis, to do some distributional analysis. We haven't really get into the AI domain to see how AI or machine learning can really help us in this regard. And as I mentioned, there's a huge amount of data set over there. And when we talk about AI, so there are opportunities of using AI. I think I don't have to get into that locus, you know that much better than me. And in the Treasury, there are sometimes there's a kind of confusion what's AI, so we're trying to actually group them into generative AI and other types of AI. There are overlap, for example, generative AI and deep learning, they sort of overlap, but we're just trying to separate them to just give our stakeholder a little bit clear idea, how they can actually use this AI for example, generative AI like ChatGPT, or use it to enhance our productivity to do some automatic analysis and so on. And I also use machine learning to actually improve our forecasting practice and do lots of behavior modeling. For example, if we increase the income tax for next year, how actually going to affect all of us, how many hours we still want to work per week if this policy being implemented and so on, just hypothetically. And lots of other things. So these are opportunities of using AI. There are lots of things we can do, but there are lots of very unique challenges, and that's something I really want to discuss today. One is that, as I mentioned, there are a huge amount of data actually within the Treasury building, pretty much covering every individual in New Zealand, how much tax you paid, where you go to school, what's your qualification, who you live with. So it's a very detailed data set. But this data set, the quality actually is sort of unknown, and in the Treasury we do our modeling based on a range of surveys, and the survey has its own problem. It really depends on how people respond. For example, in a survey we can ask you how much money you spent over the last 1 week, and you might need to think about it and just put up a number over there, and we don't know whether that number is right or wrong. And every year, basically, the survey covers different part of the country. For example, 1 year Auckland, another year would be Waikato. So it's a little bit difficult to do this kind of cross-region comparisons as well. And the next one still is around the data quality and the validation. And as I mentioned, there's no ground truth. For example, in the tax record, if one day we see one people suddenly got a tax return for 1 million, and it's sort of outlier, but we don't know whether it's true or not. So we can't just throw it away. But when we put this kind of outlier numbers into our machine learning models, and we all know that that will give us trouble. And it's also about what we really want to focus in our model. Because in machine learning model or in most AI model, as far as I know, you basically want to remove those outliers because those outliers kind of like pollute your model. But in some of our model, actually most of our model, actually that's the information we actually want to keep. We want to, for example, we focus on if we want to model, let's say, the child poverty. Then we need to focus on children actually living in poverty. But in New Zealand, this type of people, this type of household is relatively rare. We cannot throw it away. We have to keep it. But we don't have much data. Those data are actually in the middle of lots of other things that we need to identify. So how we can actually model this kind of thing is a big unknown for us at the moment. And the cost-benefit consideration, in the Treasury we've got loads of other models. And some of these models have been running for, I don't know, decades. And the reason we're still using those models is not because of how good are them. The reason is that we know how bad are they, which means that we know their limitation. We know that the AI probably have a very high ceiling, but we don't really know like the floor, where is the floor. And that's kind of thing we're trying to avoid. Like in the policy domain, we want to know like if we issue a policy, like what kind of uncertainty we can get from our model. And that's kind of thing we are facing actually is missing from some of those machine learning model. And the last one, probably the most important one, is that how we can actually convince our stakeholders to actually trust the stuff from the machine learning. One example is that from the Treasury, you got, for example, if there is a legislation, usually comes with a public submission, and the public submission comes with 1,000 sometimes. And we have to actually analyze each of these submissions manually at the moment. And we need to tell whether one submission is supportive for the legislation or not. And as you can imagine, like if we can use AI, actually it's a relatively simple process, essentially just a sentimental analysis. Then we can say, okay, whether this submission is supportive or not supportive. But we can't use it because our stakeholder doesn't trust AI. So it's related to kind of like a culture shift, a culture change. Because in terms of bias of AI and everything, it's just all over the media. Like how we can still, like in this kind of information, how we can still convince our stakeholder to actually trust what AI can provide. And that's all I want to share. So if you have any suggestions, like how we can actually use AI to improve the Treasury's practice, please let us know. Thank you very much.
Thank you. My name is Lech Szymanski. I'm from University of Otago, and today I want to quickly present this idea for a project that I'm just starting. And the idea is to try to get this bottom-up, top-down reasoning in AI in a relatively easy way using generative models that generate images. I'm not after biological plausibility. I think it's just a good idea to have it done this way, and I just want to get it done in somewhat easy way. So I'm going to start with the process of diffusion. As many of you probably know that this is how we are able to generate images using those diffusion models. And it's essentially a process where we can run the reverse process, the process of starting with an image, so having a sample of images from some distributions of images that we want to generate. We can add noise progressively to the image over some number of steps until we get all just the noise. And then we can train a neural network to reverse that process because we have all the images at every step, a little bit noisier at every step. We can train a neural network to denoise the image at each step a little bit, and then we can run this process in reverse. And it works this way, where we have some image at time n, and we have this network that takes that image and predicts the noise that was added to that image, and we can remove that noise, and then we get the next step image, and then we can do this over and over again, and we get this mapping of some starting random distribution, Gaussian distribution that is very easy to sample, and through a number of steps, we can clean it up and get image that looks nice, and it's an image. Right? And the whole point is it maps easy to sample distribution to a hard distribution. The problem with that process is that it only works one way. We can generate the images, and it's kind of sort of it's sort of chaotic. The path of the images. Of the noise to the images, it sort of wanders around in some kind of Brownian motion, and you get an image. And so people worked on this new idea called flow matching, when what they want to do is have this smoother path of noise to image, and it's done through continuous math and ordinary differential equations. There's a lot of wonderful math that I'm not going to go into, but the important part is that at the end of it, you have this neural network, which I show here as V, which approximates this vector field that takes you from noise to images, and it does it in a very simple path. It's almost a straight line. And you can sample that. It's a network that this field is continuous, but you can sample that at some number of steps, and you can generate images this way. And what I'm interested mostly is that this process is completely reversible. It's deterministic, and so given an image, you can reverse it, and you can get the noise that will generate that exact image, right? And what we usually do in practice, we add some conditioning because we're interested in generating images of some class. So you would add this conditioning C, usually some kind of vector, and that's usually added to the network as an input at every step. And this way you get to generate images of what you want. And what I'm thinking is that I want to take that conditioning and add it to the seed. So in a way, what I'm trying to do is have a multimodal mixed Gaussian at the beginning, where each mode is corresponding to a different class, and then sampling from different mode, I can generate image of certain class that I want. So in this case, a cat. And for now, I don't know how to do it, but I just simply do it by changing the mean of the image. So some number of rows is reserved, and I have this white stripe that tells me which image to generate. And that's pretty much it. And the whole point is that I can generate images of certain class, but then I can also classify images. I can take an image, try to figure out through reverse flow matching what noise it generates, and look at that mean that it generates, and have classification at the same time. And so far, I only have some preliminary results, which I ran on NIST. Everything has to run on NIST first before you run it on something useful, right? So this is how it works on NIST. Here I have number of images. So this is the noise seeded with this different white stripe. So different white stripe is a different class. And you barely can see the noise because I very early found out that the noise has to be much smaller than the conditional, because that conditional white stripe kind of has to survive all the steps to generate the image that I want. But it sort of works. So here you have these seeds that if you go through the steps of the network that was trained to generate them, it gives you plausible NIST images, right? The sort of cool thing that I'm interested in is this idea of having just the conditional, so just the mean of the Gaussian, and sort of my idea is this it's a seed for perfect image. And for NIST, it kind of works. So I have this 0, 1, 2, 3 for every digit. I have this perfectly clean image and just the conditional, and it generates sort of the prototypical images representative of their class, which I think is kind of cool, and it will be really nice if it works in general in other cases. And I can do classification. I can do the reverse process, start with an image in a test data. I can generate the seed and look at that conditional where that white stripe is and classify. And at the moment, I get about 94% classification, which is not great for this data set, but it's good enough to probably keep investigating. Thank you.
Right, yeah, we're putting together an AI framework to generate 3D reconstruction of a patient's hip in order to do surgical planning from 2D x-rays. And so the idea behind that is that surgical planning is better in 3D. So at Formus, our main product that we have out there is a 3D surgical planner. We spun out of the University of Auckland a while back, and out there, so maybe that's something we would say. But there's also some data to back it up. So yeah, surgeons, when they're doing a hip replacement, are interested in the size of the cup that goes into the pelvis and the stem, which goes into the leg bone, the femur. And yeah, in a recent trial, compared planning in 3D and planning in 2D, and the accuracy of the sizes of the implants is much more accurate when we're using our 3D planner than 2D. And yeah, getting that sizing right before you go into the operating room is yeah, really important for saving time while the patient is open on the table, which yeah, reduces a whole bunch of risks, saves yeah, surgeon's time, about 5 or 6 other people that are also in the operating room, and it does give better outcomes for the patient if that plan is more accurate as well. Surgeons are also moving more and more towards robotics and navigation to improve the precision of their work, and you can do much more, yeah, you have much more capabilities with the robot if you have done your plan in 3D than in 2D. And we also find that that surgeons just like to visualize the patient's anatomy in 3D before they go into the operating room. It helps them prepare in sort of a qualitative way a bit better. So that's what this person's doing. At this stage, not everybody plans in 3D, and the reason is that imaging is much easier in 2D. If anybody here has had to get a CT scan, you know that the wait times can be pretty long. The cost is quite high, and yeah, so there's a barrier there. CTs also are additional radiation exposure, so a lot of, yeah, it's a trade-off that people have to make. And also surgeons are interested in the posture of the hip joint while you're using it. So CTs, to get a CT scan, you generally have to be lying down, whereas X-rays can be done standing up. So there are advantages to the X-ray in that case. So yeah, our aim with this project is to combine the benefits of the 3D planning with 2D imaging. For yeah, when we get there, it'll be sort of the first opportunity ever to get a 3D plan from a standing pose, and yeah, to just have all of the best of both worlds, basically. So yeah, reconstructing 3D geometry is a project that lots of other people are working on. Yeah, this is taken from a project by Tencent. In their paper, they compared a few different models where you provide just one single image and it will produce a 3D mesh with, yeah, these days pretty incredible detail. Even though the image is just from the front, it will, you know, figure out a reasonable representation of what's on the back. So, yeah, some really cool models. We want to do something similar, but for surgery. So these models often use sort of diffusion, potential to hallucinate. We need sort of more, yeah, quantitative models. We also need quite high resolution for the pelvis. The pelvis is relatively large, and we need to take measurements on fairly small scales. And these are sort of brand new. A couple of years ago, these didn't really exist, and slowly they're, yeah, people are starting to port them across into the medical space. At this stage, they also tend to work with visible light, so they expect the light to be bouncing off the surface, whereas obviously with an X-ray, it's passing through. So there's a different physics involved. But yeah, eventually we want to do something similar. This is our 3D plan at the moment. You can see it moving around. Part of the thing with the light passing through the object is that we also want to get information from the internal geometry. So there's my mouse. This is the cup, but this white region inside the femur is really important because that's where the leg implant goes into. So we not just interested in that in the outer boundary, we're also interested in sort of the inner boundary. So it's quite different to these models and does require some adaptation. So what we've got at the moment, I've got an AI model that's been trained using CT images with matching ground truths, and from these CT images we can generate synthetic X-rays. So yeah, over on the left-hand side, the top one is a real X-ray, and the bottom one is a synthetic X-ray. yeah, if you look closely, you can spot the difference, but on some level, they're very, very similar. And yeah, that allows it to be, so we think, well, we've aimed to get the realism as high as possible, and then we can add augmentation. So this bottom image is varying just a couple of the parameters to look at different x-rays that you might get from different labs or different radiographers or different brands of x-ray machines. They come out looking different. And then we can generate x-rays from whatever angle we want. And so we chose these three angles from in front and then from 45 degrees either side. And yeah, trained a neural net architecture to transform those 2D images into a 3D geometry. And it comes out something like this. It's the error compared to the ground truth. And to output that takes a large amount of memory. So yeah, we're using the biggest GPUs we could get access to. At this stage, then we can plug it into our existing planning software, and we can compare the plan from a CT and plan from the X-ray. So you can see there's a little bit of a loss of detail between the CT and the X-ray, but perhaps, yeah, better than expected. If you compare the sizes of the implants, you've got a size 6 versus a size 7, and the cut comes out more similar. So yeah, we're very happy with that result. So we trained an AI model to reconstruct the 3D geometry and integrated it into our existing planning software. And yeah, the measurements and the recommended implants are similar to a plan generator from CT, and we're working towards clinical trials. We've actually just in the last couple of weeks had some surgeons come on board that they're willing to try this out, do their normal planning, and then try our plan as well, and then we'll be able to push out and see where we go from there. Thank you.
My name is Pfeiffer. I'm from Massey University, and I'm not actually a computer scientist, but my background is more in game theory and behavioral sciences. And as you can imagine, large language models had a huge impact, especially since the OpenAI models came out in 2003. And so one of the key questions that comes up in the behavioral sciences is, with the language models, is whether language models can be used to generate synthetic research participants for behavioral science studies. If that works well, it can offer the field substantial benefits, because the main constraint in things like experimental economics or psychology is sample size. So you have to get a lot of people in if you want to run a lot of different behavioral settings for your research question. And so just to give you an idea, at the Decide Lab at Oakland University, we can run studies with about 500 participants. If you run an online study, you are in the 10,000s, but with large language models, you have basically no limitation on that end. The key question is, of course, that, are your responses from your language model sufficiently similar to human subject responses, right? So that's basically the critical point in the field. And so I'm investigating these things in the context of deliberation and collective decision making. So deliberation, think of that as a careful, reasoned consideration of different options or arguments or viewpoints before you make a judgment or a decision. And of course, inter-agent deliberation is of huge advantage when it comes to collective decision making. And so that, of course, in economics, there's a huge literature, in particular in terms of epistemic democracy on this topic. But also since 2003, we have a bunch of very interesting papers coming out where large language models basically participate in deliberation processes, that may be in the form or in the role of facilitators, as participants, also participants on behalf of a human user. So all these roles are being explored. So one key property, one key functionality of deliberation is information aggregation. And so I have that here. Let's say we have two agents, right? And they have to pick a restaurant. And so I denoted those by R1 and R2. And these agents have been to these restaurants, and let's say our agent A had a pretty good experience in restaurant 1, but a more mediocre one in restaurant 2. But our other agent has different preferences, different experience, has a more mediocre kind of experience in the first restaurant and a very good one in the second one. Now basically what you want to do then, you want to bring this information together. You want to make a decision that basically both agents are aware of the other's experience, and then you basically come up with the best possible decision given the information that is around, right? And in an ideal deliberation, this is what's happening. So our benchmark of information aggregation is whether your deliberation outcome mimics the choice of an agent who has in possession of all the information that is around. Okay, and so we can actually do that. So, like, I mean, implemented that I started with GPT-4 models. I'm now using generation 5. So the single agent choice given a piece of information is a single prompt, basically. For deliberation, we simulate that by putting private information into the system prompt, and then basically use the information exchange between the agents through the user prompt, and we do it in a way that we pipe a response of one agent into the dialogue, right, and it serves as an input for the next agent. So we can basically generate synthetic dialogues. And we use that for various scenarios, use a baseline setting for basically free-form deliberation, but then also can use specific protocols, such as like Anderson-Holt has a pretty specific information cascade protocol, or also can sneak in counterparty characterizations. You can say to one agent, like, look, you don't trust the other agent, or you really trust the other agent. And that can undermine your information aggregation, and that's sort of a typical study question in the behavioral sciences. Okay, so that's like quickly running you through the results, so I don't give you any quantitative stuff because we probably won't have the time for that. You see here a dialogue that comes up, typical dialogue. It's like they're settling on a restaurant called Dance Dance, so all of these restaurants are of course fictional. But what we basically can show with that is that language models are pretty efficient in aggregating information through dialogue, through the simulated dialogues. Language models are pretty prone to information cascades. So that's like information cascade as a protocols that we're using there. They have very, very, very constrained information flow. And that basically is known to go information astray for human users, but we see the same problem popping up with language models that are deliberating with these protocols. What we also find is surprisingly small impact of counterparty characterization, so that's something where I would expect that would play more of a role if you play that with human users. But if you say don't trust the other one, it doesn't really affect deliberation outcomes, even so I would expect that to happen for human users. Okay, so where are we going with that next? I mean, I'm still running a whole lot of simulations to assess how reasoning parameters and things like that affect deliberation outcomes. But there's certainly, so what we're doing right now is independent noisy signals that are being aggregated, but there are much more interesting scenarios. So once I understand the independent noisy signal aggregation, kind of probably move into more interesting scenarios. Communications then, as you might know, has also a lot of strategic components. So we have in economics, we have sheepdog models, we have bullshitting and bluffing and all of that. And that's going to be interesting to see how language models perform there. And then experiments, and then at some point possibly also scaling that to population size models. Good, thank you very much.
Right, good afternoon everyone. My name is Nguyen. I'm from University of Wellington. And today I'd like to talk about one of our recent work, which is to use multi-task genetic programming for emulating AINZ models. So what's the problem? The problem is we are losing a lot of ice. So mostly from Greenland and Antarctica, and we are losing about 1,500 gigatons per year. It means that if all the ice on the Earth is melted, then the sea level is going to rise about 70 meters. Of course, we are not going to lose this now, but even a fraction of that can also have a huge impact. So if you look at this figure here, that is the impacted regions of Wellington when the sea level rises about 5 meters. So we lose all the coastal area and we lose the whole CBD, including where we're sitting now. Okay. So it's important to understand how ice is melting. And one of the ways to do that is to base on the physical ice sheet model. And the most common one is parallel ice sheet model, or PISM, which is commonly used by the whole community. But the issue is that PISM is computationally intensive because it had to solve a lot of equations with lots of constraints. Okay? And therefore, we cannot run PISM for long-term prediction or simulation. So the goal of this research is, well, we would like to develop machine learning models that can emulate the PISM accurately while using very low computational resource, so that we can run long-term and large-scale simulations. So to do that, firstly, we use PISM to generate 286 years of data with high resolution, so 761 by 761. And we generate also climate features, including precipitation, air temperature, ozone temperature, bedrock elevation, and we also extract the spatial features and temporal features. Based on all those features, we aim to build machine learning models that can predict both ice thickness and ice velocity. And that can tell us how much ice we are losing every year. So here is the overview of our system. Very much we have two stages. Okay? The first stage is classification. And given a region, we would like to know whether we have ice on that region or not. If we have ice, then what kind of ice it is that grounded ice or floating ice. Okay? Once we know that, the second step is to build the regression models to predict the ice thickness and ice velocity. So you can see here we have two tasks, right? One is to predict ice thickness, and the other one is to predict ice velocity. So we use two prediction functions for that, and we represent those functions at a tree expression. Why? Because trees are easy for people to understand, so more interpretable. And we use geometric programming to involve or to optimize the two trees. And during the learning process, we allow the knowledge between the two tasks to be exchanged, very much transfer learning between tasks. So hopefully, by doing that, we can improve performance on both tasks. So that is the general idea. And here is the key result for ice thickness and ice velocity on R-square, mean square error, and root mean square error. In general, we achieve very low average errors for both ice thickness and ice velocity. And compared with other machine learning algorithms, including deep learning, the model achieving about 5% to 15% improvement. Okay. So, key takeaway, we can see that we can use geometric programming to build an effective, efficient, and also more interpretable models for emulating ice sheet models. And the future work can be, we can consider more learning scenarios. Currently we have only one learning scenario. And we also can find a way to extract more effective features. Hopefully can further improve our performance. That's all. Thank you.
Hello everybody, I'm Fangfang from Center of Data Science and AI, University of Wellington. Today I will talk about how can we make a smarter decision. So everybody, every day, we need to make a lot of decisions, right? For example, every day we can have a breakfast and go to work, or go to work and then have breakfast. All these kind of problem are kind of a scheduling problem. And that's my research focus. And today I will introduce a hyper-heuristic approach. How can we learn some rules we can use to make a good decision? As I mentioned before, I focus on planning and scheduling problem. Here is another example. This is one of the popular combinatorial optimization. For example, in the conference, we have a lot of volunteers, and volunteers have different time constraints to do this work, right? We have a lot of people here, and we have different time. How can we make a good schedule? This sounds quite easy, but actually quite hard. Especially there are many people, and the time are different, and some people may change their demand. And how can we schedule? Normally, when we do this work, people can do manually. It's quite time-consuming and quite frustrating, right? It's probably one of the biggest headache job in the world. And how can we do better? In traditional way, like how can we make this kind of decision? If we take another example, like the flights at the airport, believe most of you have the experience, like we delay at the airport, right? It's a very bad experience. So how can people make a decision? Normally we can have an initial plan, right? We schedule, if at the airport we have the flights, and also we have the gates, right? How can we do this kind of schedule? And there's a lot of dynamic events, right? About the weather, different dynamic events can affect the plan. So we keep updating, and we need to communicate with others a lot. It's a kind of a loop. We keep doing this process to make the final schedule. But the goal is when we want to minimize the delay, right? How about we use another way to make a decision? So traditional way, we manually have the original plan, and we keep updating and communicate with others. Another way, like I introduce the hybrid hearsay learning, you can consider in this way, right? So normally when we handle one problem, we give the solution directly. For example, we know the processing time of something, and the schedule try to tell people when to do what. So we give the solution directly. But another approach we normally use is rules. And people are good at using rules, right? So if people ask you to make a decision, you can say, first come, first serve, right? I shall see the processing first. And the first come, first serve is quite popular used in our daily life. And these are rules, but these rules are easy to use, and people kind of understand this rule, but it's not effective enough. So how can we learn a rule probably like this, which looks complex but more effective? Of course, the interpretability is another issue. And how can we learn this rule? We can use a hybrid hearsay approach. This approach is trying to selecting or generating a comprehensive rule to handle the problem. So this is a hybrid hearsay learning. Why we use this approach? You probably already have some idea. It's easy to handle large scale problems. So no matter how many people waiting there, we follow the rule. I always can have the solution quickly, right? It can react to dynamic events efficiently, right? If someone quit, you still have the solution, and it can handle multiple instances. It cannot only use in one scenario, can use in another scenario, and easy to implement. And if we have some domain knowledge, we can incorporate with the rule, like the VIP first, this kind of rule. It's easy to incorporate. And we already work on different projects, and here are some examples. One is the tugboat scheduling at the port. So when a big ship comes to, for example, Wellington, you can look at the Wellington harbor, and we need the tugboat to, drag the ship to the berth. So how can we optimize this task of the tugboat to reduce the energy consumption? And another project that we are working on is the ambulance dispatch at Wellington. So we have a collaboration with Wellington Free Ambulance, and how can we, when someone calls the ambulance, how can we make a good decision? And also like some workflow scheduling, this kind of real world problem, and we are working on. So the takeaway message here is we are good at using rules, right? And the simple rules are not effective. How can we learn a better rule to help us to make a better solution, which actually can make our life better? This is my research. If you are interested in, we can talk later. Thank you.
Hi everyone, my name is Varvara Vetrova, and I was in Canterbury University, and now I'm heading from Australia. And so I'm going to talk today about sea surface temperatures anomalies and how to predict them. To begin with, why do we need to actually care about sea surface temperatures? The reasons are multifold. Well, basically it can damage aquaculture, it can lead to loss of some habitats. And actually, such loss is preventable. So if we know in advance that marine heat wave is going to happen, then we can act accordingly and prevent a situation like this. Just to give you some example of notable marine heat waves around the world, starting with around Tasmania. Basically, in 2017, a large marine heat wave loss, kind of caused loss of habitats and for kelp forest around New Zealand. And another notable heat wave of the coast of North America in 2015 also caused damage to ecological habitat. If you want to predict such events, we need some data. And the data is coming from different sources, such as remote sensing and in situ measurements. I was particularly curious to discover that it's actually possible to collect data by attaching sensors to marine mammals. Fortunately, we do have tools to help us to mitigate all these different data sources. And one of them is reanalysis, which is commonly used in such problems in climate prediction. And basically, it's aggregated observations around the globe. Because we have grid observations, now we can think about what kind of tools might help us to predict marine heat waves or sea surface temperatures. And some classical machine learning tools which can be used are convolutional neural networks, for example. However, there are some drawbacks with convolutional neural networks or their variants, like combinations of convolutional neural networks and LSTMs. In particular, the drawbacks lie in the fact that climate is interconnected, and we would like to take into account the fact that what is happening around, let's say, north of Pacific Ocean might influence processes far away. So how we can mitigate such drawback? Basically with the help of different data structures such as graph neural network, in which we transform our observations into gridded data. By transforming sea surface temperatures into grids, we can take into account the teleconnections. And here's an example of 3 such nodes with sea surface temperatures observations connected to, you can see, quite far away region in the ocean. By converting our gridded data into graph representation, we can improve performance and take into account this physical processes happening in the ocean. So the workflow in a nutshell is basically we have observations, historical sea surface temperatures, we convert them into grids, and then we convert grids into graphs. And through machine learning approach, we predict the sea surface temperatures on a global graph in each node. Now let's talk about what is happening behind the scenes here. Basically, we have integrated graph neural network diffusion model, which help us to predict sea surface temperatures from 1 month to several months in advance. And from sea surface temperatures prediction, we can achieve prediction of marine heat waves because they are defined basically as sea surface temperatures above a certain threshold. I'm not going to go into too much details about the models. If you're really curious about them, you're very welcome to ask me later, but I will show you some results. So basically, with help of such models, we can predict better, at least in simple persistent models, most parts of the globe. And in this case, the red dots indicate better prediction than simple baseline. And the more intense color is the better prediction is. And the blue dots represent worse prediction than the baseline. And we did look into worst predictions from marine science point of view, and we found out that actually here we don't have that much seasonality, and that's probably why we have worse predictions here. Similarly, we can predict anomalies and convert them to marine heatwaves prediction. Also, the question was, well, we do have physics-based models, and can we actually predict better than physics-based models? And we ran extensive comparison with dynamical model Ensemble. It's a suite of models which basically predict also sea surface temperatures, but it takes a very long time to run those kind of models. And we found out here that we have better predictions in certain areas. As an example here, blue color indicates correct prediction, yellow color indicates correct prediction, and blue color are the errors. And we have less errors in Tasman Sea. Where to next? Well, basically, we can think about precise models for particular areas of the ocean. At the moment, we are looking into issuing a heatwave prediction and prediction of enclosed water bodies, not just open ocean, such as fjordland. And also, the other question is, well, we have this all vast information. Can we actually find insights what is driving these marine heat waves? And that's what we are planning to do next, to find the drivers of marine heat waves and find longer lead times as well as an option too. Thanks very much. That's all from my side.
So I did consider removing this weird Borgified John von Neumann, but what the heck. Right, so going to talk about a system that we've been building in my lab. And that system has sort of two purposes. One purpose is to provide a platform in which we can integrate the results of some fundamental AI research that we're doing and the sort of fundamental AI research that the rest of you are doing, including potentially some of the research which has been talked about so far. And the other purpose is to provide agentic assistance in the scientific process, starting with the AI research process so that we can act at greater scale. And acting at greater scale is kind of important. Most significant AI research programs around the world at the moment, the ones with really high impact, are done by quite large teams. And these teams are difficult for a country like New Zealand to marshal, both because of our limited population and also sort of by implication because of limited funding. So we're limited in scale in large part by the availability of people with the expertise to work in large teams to achieve dramatic impact on AI. There's plenty of impact in New Zealand, but we are not having the sort of impact that, for example, DeepMind or DeepSeek are having. And this is a problem that if we can, well, why not fix it? So we are we built a neurosymbolic system that combines the strength of LLMs with a very flexible sort of representation scheme. It's not a knowledge graph, it's a knowledge representation system that all it's depending on is the notion of explicitly represented knowledge, and that explicitly represented knowledge could be in natural language, or it could be in a logical formalism, or it could be in a graph formalism, and it could be or any of those formalisms augmented with, for example, an embedding or multiple embeddings to help manipulate them. So the idea is to build grounded AI that is both flexible and knowledgeable. And in particular, it supports complex organizational process and domain models, and it assists with the process of eliciting and structuring those models. So the ultimate idea is that you power up the system in your lab, and it talks to you, works out what the process of your labs are, and gradually gets good at helping with them, including, we're amongst friends, so including the process of dealing with your organisation or university, which can produce significant overheads. Right, so the idea is, so one workflow is dealing with papers. So every morning I read a bunch of papers, abstracts, and I send them out to, I save them in paper pile and I send them out to my PhD students, and occasionally they'll pay attention. It would be nice if that process could be done at greater scale and taking closer account into the current state of the students' work. So the idea is have a flow which imports papers from the sorts of sources that I'm looking at them, annotates them with the entities involved. So, for example, the knowledge that the paper was produced by a fellow New Zealand researcher, so it might be a source for collaboration as well. Verify that either by asking a person or, as the system becomes better, by verifying it itself and then synthesizing it into a suggestion for a follow-up action. And as this is going on, the system should be continually learning, fine-tuning models, using reinforcement learning to get better at each of these steps and to reduce the cost of these steps. So it's using the simplest system which will actually perform them well. So here's an example of the system learning about a paper. So I asked it to look up about myself and tell me about my papers. It uses MCP to access its own knowledge base. So it's introspecting on its own knowledge base. It's telling me about a paper that I wrote a very, very, very long time ago, before any of you were born. And then it is, you can click on that paper and it will take you to a concept for that paper. So it can introspect on its own knowledge and it can add to that knowledge. So here's a workflow where here's a considerably more recent paper, actually calling for a more knowledge representation. I am partially bought into the idea of more explicit knowledge representation, and I contributed to this AI magazine paper. And then the process is, find that paper, then at the moment paste the list of authors into the system and ask it to create a knowledge representation for all of those authors based on that list, which it does autonomously and permanently. So it's now got a model of the co-authors of this paper. The hope is a collaborative engine for building a unified knowledge research assistance program for Aotearoa by federating these platforms together. So privacy for your own personal data, privacy for your organisational data, but the ability to share it between sites automatically, producing a common language and also sort of systemic support for working together so that when there is someone that we should collaborate with, I've recently been talking to a lot of people in the New Zealand AI research community and having assistance for knowing who's working on stuff which is relevant. I've noticed synergies, because of that, I've noticed synergies between papers which were presented here or talks that were presented here where people might not be aware of it. People are working on related things, and even in a small community like this, they might not be aware of it. We can automate the process of helping ourselves with it. So we have built a system called John Van Neumarkt. You can send an email and ask it about itself. It won't reply at the moment. You can also send me email, and anyone who knows me knows that there's a reasonable chance that I won't reply either, which is part of the reason I've been building this with people. Just as of yesterday, it's available as an open source project, so you can download it and install it and run the setup script, and there's a good chance it won't work, but in the next few days it will start to work, and we very much would like people to contribute to it. One use case that I'm particularly keen on is writing an MCP wrapper for Weka so that this system can do some of the sorts of things that Albert was showing us in the online version of it. So that's it for now.
And anyway, I was at this conference and this guy said, well, AI is just algorithms. So I don't know what people are so excited about or worried about. And there we go. And I thought, well, you know, yeah, it's coding. We're instructions. So, that's not rocket science. That's science, and nobody understands consciousness, and there's not a really good definition of mind. And I thought, well, what difference does it make if the code, through kind of chance and bad experiences, evolves and changes and gets more complex over a couple billion years, or if it goes faster? The whole thing is it's evolving code, creating complexity that interacts with the outside world and creates information. And you got to forgive physicists. There's a physicist that she works in trying to figure out what life is. And one of her definitions is it's complexity that generates information that performs work. And, you think about that kind of stuff, and it's like, well, okay. So it doesn't matter privileging the biological, or do you look at what happens, what it does, not whether it was made in 20 years or made over 3 billion years? Is that stuff even relevant? And then I don't know if you guys have run into this guy, Jeff Hawkins. He's a neurologist that works on the theory of mind. Richard Dawkins loves him. And he's, well, you can just read it, developed his own research institute. He went to MIT and then he went to Berkeley, and they were all working in little silos, and he wanted the whole thing. And when you read what his work is, it's like you're stoned. You're going like, wow, this is amazing. But, the brain is, instead of just like intertwined, actually has stacks. And it just sounded, when I was a long time ago, did computer stuff, I go, ooh, this just sounds, kind of parallel. So anyway, I thought, I don't think biology, it's like anthropomorphism. We privilege biology, but that's really not the thing. If we found it some other way, it's the function. So is it coding that's the foundation to life? Don't know, but it creates something that it's complex and makes information that does work. And then the other thing that people worry about is, are we making a bit, are we on the verge of doing something that people 300 years will look back and say, how could you, in a number of ways? Either how could you be so stupid, or how could you be so blind? And so if coding is creating something, that's why I asked my poor victim what sentience was, because nobody really knows. What would be that something thing that would make us not only have to recognize that this is something akin to life, but it's something that we have to take moral consideration of? And then what would it be if you're morally considerate? Not everything that's morally considerate we hold responsible for what it does. There are a lot of things that are morally. What would it be for something to then be not only morally considerate but held responsible? Or would the creator always be responsible? And then you think of the harm done by social media platforms with no responsibility. Don't know, but if something becomes autonomous, dogs are autonomous. We don't hold them responsible, but we certainly enforce penalties for harm. So anyway, so you've got these things about what would be sufficient for moral consideration and for responsibility. And autonomy, agency, rationality. And then the other thing people worry about is AI getting out of control and, becoming a threat to humanity. And there is, I'm sure you guys read this too, instances where people try to shut down LLMs and they resist. And sneak in things that aren't explicit instructions, and they report experiencing intrusive thoughts and things like that. So that's kind of interesting because they're not even what people think of as general AI, but that complexity is doing something and we don't understand exactly what. And then with quantum computing, I don't know if you guys follow stuff, but there are studies now that our brains do things on the quantum level as well. Serious, recent things. And, just interference, interactions. So that, it's just like there's some parallels and there's obvious differences, but are the differences relevant? And should we look at function or form? And I tend to look at function rather than form. And then people are concerned about harm. And, one obvious harm is the big energy use for a lot of trivial things that we don't need to use energy for. But malfunction, human-directed harm, and then autonomous harm. And I wonder about the concern for autonomous harm being rational. Because if you think about it, we biological creatures, Richard Dworkin with the selfish gene, we are programmed to survive, to compete, and to reproduce. That's part of our coding. But that doesn't have to be part of AI's coding. And does humanity's aggressive, tendencies that we worry about AI doing to us come from complexity and intelligence? Is that intrinsic to intelligence, or is that intrinsic to our coding of survival, reproduction, resources? So I kind of think, Benjo thinks that if we made an AI that wasn't programmed to have any specific goals, it wouldn't have any driver to do that. And if you were really intelligent and didn't have the drive to reproduce, compete, and survive, what reason would you have to get bigger or to get more powerful? Or that, those drives for power, those are based on, basically sex. Or is it based on intelligence? I don't know, but I wonder, I think humanity so far hasn't managed to avoid things that are very dangerous and harmful to a lot of people, only avoided so far the ozone layer because it would kill us all. And I don't even know that we avoided it because it would kill all people, but it would kill nation states. And that's how people manage to cooperate, not to save humanity, but to save their own nation states. And nuclear weapons. But nuclear weapons aren't independent. So I wonder if the real concern that we need to worry about with AI is not that it gets really smart or smarter than us, however we define smart, but human misuse of it. Because at least I suspect, I don't know, but I'm pretty darn sure that development by nation states will proceed because it's advantageous to those biological drivers of competition, survival, resources to have the better one, the more effective one. Yeah, scary as. And so I wonder if AI doesn't have those drivers, is the enemy that people need to really be scared of AI independent or our use of AI? And is there any way to constrain that other than AI? So I don't know. These are just questions, do philosophy of law and stuff like that. But yeah, thanks. I think that's it.